Good afternoon, everyone. We are very happy to welcome you all to this session of the Gaza Excellence Talks, which, as you know, is a series of high-level scientific talks co-organized by our NGO, Academic Solidarity with Palestine, and three universities in Gaza, Al-Aqsa University, UCAS, and the University of Palestine. Today we're very fortunate to have the presence of two of these three Gazan universities. The third one could not be here due to internet problems in Gaza. So I will give the floor to them. We are very happy to see you all. These talks are scientific talks in solidarity with Gazan scholars and Gazan students. Our heart is with them at all times. Uh, if Nadine, if you would like to say a few words about the University of Palestine, that would be very appreciated. Thank you.
Yeah, thank you very much, Christine. I'm really delighted to be here today with you. And I will start by thanking the Academic Solidarity with Palestine for organizing such an event. And I want to especially thank Dr. Anne for having her today. I'm pretty sure that it's going to be a very insightful talk. We, as a University of Palestine, we did our best to go on with our online learning and teaching during the war, and we are still going on until now. We've got challenges, we've got difficulties, but we up to that all these challenges, and we're gonna keep going on. And with your help and with your talks, I think you are giving us like a kind of a push that you are there for to help and to support. So thank you very much for having us as a University of Palestine, and I hope that we're gonna continue in that kind of collaboration. So that's me. Thank you very much.
Thank you, dear Nadine. Asma, for the University College of Applied Sciences in Gaza.
Hello, everyone, and I'm so delightful for this participation. I'm representing the University College of Applied Science in Gaza. It's one of the largest technical colleges in Palestine. It also serves approximately more than 11,000 students across more than 60 disciplines, offering bachelor, diploma, and professional diploma programs to meet the urgent demands of the labor market. Actually, the university was established in 1981 with a decision from the Ministry of Higher Education, and UCAS was initially named the Community College of Applied Science, and then the name was changed. Like the other universities, unfortunately, my university was leveled to the ground, but not the ambitions and desires of the academics as well as the students. And now we are approaching the fourth semester. We are studying with a full energy online with the hope that we will restore our buildings and ambitions and hope quickly. It's not easy as it is, but the determination of our students give us more persistence to work for them every day. I'm so delightful again for this opportunity, and I know that it will have very important perspectives for education, not only in Gaza, but the worldwide. Thank you very much.
Thank you so much, dear Asma. This talk again is in the name of the universality of science and in solidarity with Gaza. I will now introduce our speaker today. We're extremely happy to welcome Dr. Anne Huillier, and I'm all the happier that it is the first female speaker in this series. So it's particularly important. Dr. Anne Huillier is a professor at Lund University in Sweden. She started her career at the Commissariat à l'énergie atomique in France. In 1995, she moved to Sweden to Lund University, and she was awarded the Nobel Prize in Physics in 2023, together with Pierre Agostini and Ferenc Krausz, for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. The title of her talk will be The World of Atoms at the Attosecond Timescale. And dear Anne, thanks again for being here with us. and for this talk. And the floor is now yours.
Thank you very much. I'm very happy to be with you today. So this talk is about attosecond timescale, and let me start by telling you what is an attosecond. It's 0.1701 10 to minus 18 second. It's very, very small. And actually, if you on this slide you see many timescale. You have the age of the universe is approximately 10 to 18 seconds. So you have as much from the age of the universe to the second than from the second to the attosecond. So as I said, there are several timescales on this slide. Humanity timescales, astronomical timescales, the heartbeat, this is 1 second, mechanical timescale, milliseconds, electronic timescale, nanosecond. Timescale for that you need to observe motion of atoms in molecules is femtosecond, 10 to minus 15 second. And the science of using femtosecond for looking at atomic motion led to a Nobel Prize in chemistry to Ahmed Zeeval in 1999. If you go to the next time scale, attosecond, this is the time scale that you need to follow electron motion in atoms, in matter. And this led to Nobel Prize 2 years ago to Pierre Agostini, Ferenc, Krausz, and myself. And this is the story behind this Nobel Prize that I'm going to tell you today. So this is the outline of this talk. I'm first going to tell you about high-order harmonic generation, then attosecond light pulse, and then an application, how we use these parts to study electron dynamics. Nothing would have happened without the invention of the laser in 1960 by Theodor Meinmann. The invention of the laser led to new field of science. One of them is nonlinear optics, where new frequencies of light can be generated by interaction between light and matter. On this slide, you have a picture of the experimental setup that was used by Peter Franken that led to the second harmonic generation. So what you see is a laser focused into a piece of quartz, and then the light is analyzed by a prism and is observed, of course, the fundamental light, but also the second harmonic. Another field which was created thanks to the invention of the laser, very fundamental field and very small to begin with, is the field of atoms in strong laser fields or multi-photon processes. On this slide, you see a 2-photon excitation process where an atom absorbs 2 photons to be excited. And actually, it's very interesting to note that these processes that could only be observed after the invention of the laser were predicted theoretically already in 1931 by Maria Goeppert-Mayer as an exercise in quantum mechanics. In the 60s, Russian scientists studied multi-photon ionization processes where an atom can absorb several photons and be ionized. In 1979, my colleague Pierre Agostini and co-workers observed what is called above threshold ionization, where an atom absorbs more photons than what is needed for the ionization. And it's possible to observe these processes by looking at the energy of the electrons. My own thesis work, that was at the beginning of the 80s, was to look at multiple ionization processes by multi-photon absorption. Here you have an example showing the production of xenon 2+. So at that time, it was thought that in this interaction between atoms and a strong laser field, you can produce excited atoms or excited ions, and it would be interesting to look at the fluorescent light that could be emitted from this species. So at that time, I was a young researcher at Commissariat l'Énergie Atomique, close to Paris in France. So we set up an experiment where we focused an intense laser pulse into a gas of atoms, and we observed the light using a grating. If you don't know what a grating is, it is like a prism. It's optics to analyze the radiation, and then you have a detector. What did we see? Well, we did not see fluorescent light. This is the beauty of experimental physics. Sometimes you observe something new and unexpected, and this was the case. So what we observed was the generation of high-order harmonics of the laser. This is a spectrum obtained in argon gas, where you see peaks, and the frequency of these peaks are multiple of the laser frequencies. Only odd multiples. Here you can see, for example, harmonic 13 up to harmonic 31. If you plot the distribution of these harmonics as a function of order, you observe a characteristic behavior with a plateau, which means that all of these harmonics are more or less the same intensity, which ends up with a cutoff. And maybe the most important part of the discovery was the fact that we had this plateau where all the harmonics had the same intensities. The reason is that at the time we were thinking very much in terms of perturbation theory, where you expand the polarization in the medium in terms of a series of powers of the electric field. And for such a series to be valid, you expect the first order to be much larger than the third, much larger than the fifth, etc. And this was obviously not the case. So it was a non-perturbative and highly nonlinear phenomena. If you look at the electromagnetic spectrum, which is shown on this slide, going from the radio waves to X-rays, where are we in the spectrum? The laser is usually in the near infrared or visible range in this region here. And then we multiply by a high integer so that we end up in a region of a spectrum which is called extreme ultraviolet. In this region, of course, the light is not visible to eye, and it's also strongly absorbed by matter. It strongly interacts with matter, which makes it interesting. But that means that in order to study this light, we need to work in vacuum. We need to evacuate around the experiment that we use. Now, if some of you are a little bit lost, I'm sure you have heard about harmonics in music before, and here is the sound that you make when you play the violin, and you play one tone, and you get not only the pure tone but also harmonics of this tone. And depending on which instrument you play, you can get more or less harmonics of this instrument. You can compare with harmonics of light that we produce. And actually in both cases, we have a strong interaction here between atoms and the laser, and for music, in this example, between the string of a violin and the bow. Of course, in music, we are talking about acoustic waves, while I am talking about optical waves. So very different type of waves and different frequencies. here we are in hertz, and usually we count in terahertz, sorry, in petahertz and even higher. In order to understand the physics behind, we need to understand both the interaction between an atom and the strong laser field, and also the interaction between the medium of atoms and the laser field. So on the left, I am showing you how to describe this, the single atom response. You need to solve the Schrödinger equation that you can see here. And what you have on the right term is the atomic potential for the electron, and then you have the laser atom interaction here written in the dipole approximation. The difficulty is that this laser atom interaction is strong. It's comparable to the atomic potential. But you also need to solve the what we call the many atom response. You need to consider the emission from an ensemble of atoms in a finite medium. And in particular, in order to have efficient harmonic generation, you need a certain phase condition to be fulfilled. This is called phase matching. You need the waves emitted by all of the atoms in the medium to add in phase, as it's shown on this figure. This is described mathematically by Maxwell equations, which can be simplified to a wave equation, as you see here. Here you see how a field E is generated from polarization in the medium, and this polarization is coming from the solution of the Schrödinger equation, is the ensemble of this single atom response. Actually, the first attempts to understand our results were to numerically solve these two equations. Efforts which were reasonably successful, but doesn't mean that you understand the physics. I'm continuing this talk a little bit historically. Now we are in the beginning of the 90s. We work on making new and dedicated instrumentation to study these processes. And here you see an old photograph of myself and my first PhD student, where we build the instrument that you see. So here you don't see the laser, it's behind the wall here, but you see a tube here where the gas is coming. Usually we use rare gases. And then you have vacuum chambers, which we need again because this radiation is absorbed by air. And in these chambers, you have optics, as is shown on the scheme, enabling us to separate the different components, the different harmonics. And finally, you have an electron multiplier, which is a detector of the emitted photons and which is sitting here. And also during this time, there is really a huge progress in laser technology with the discovery of the chirp-pulse amplification technique, which was done by Gerard Moreau and Donna Strickland, and they got the Nobel Prize for this discovery in 2018. And also a new laser material called titanium sapphire. And here in Lund, you have one of the first laser in Europe and actually in the world built on this principle, combining titanium sapphire and chirp-pulse amplification. And this led us, myself and my student, to actually collaborate with Swedish scientists to move our equipment to their laser facility and to perform experiments. And 2 years later, I would actually move to Sweden, and from 1995. So now I'm coming to the second part of this talk, which is about attosecond light pulses. The idea that this radiation, composed of high-order harmonics, would lead to attosecond light pulse, came up very rapidly, beginning of the 90s. And I'm illustrating the idea on this cartoon. So what you see here are 3 waves corresponding to 3 different harmonics. Let's assume that these waves are phase-locked, which means that they are in phase at a certain time. In phase means that, for example, here, the maxima coincide in time. Because of the periodicity of the interaction, after half a laser period, which is 1.3 femtosecond for the laser that we use, the minima will coincide. And again, after another half laser period, the maxima will coincide. And again, the minima will coincide and the maxima will coincide. If we now sum these 3 waves, we obtain an electric field that looks like shown here. So it's a series of short pulses of light. Why is that? It's because when the 3 waves are approximately in phase, then you have constructive interference, while when they are not in phase, we have destructive interference. So you see that this allows us to confine the light into short period of time. And the duration of these pulses is typically a few hundred of attosecond. We are in this attosecond time scale. What is shown at the bottom is the intensities of these pulses. If we now sum not only 3 waves, but 10 waves, 10 harmonics, and we suppose that these 10 harmonics are phase-locked, all coincide at a certain time, the maxima coincide, then again, because of interferences, you can get even shorter pulses. So this was an extremely interesting idea. Is it possible that we have this phase locking of the harmonics? In that case, it would really open up a new time scale for humanity, the Attosecond time scale. So this question was raised almost immediately after the discovery of the higher order harmonics. It took the community 14 years to be able to answer this question, of course, by the affirmative. One breakthrough in the understanding of the physics was due to theoretical discovery of what is called the 3-step model, and which is illustrated on this cartoon. And this was due to Ken Kullander and co-workers and Paul Corkum, 1993. So what you see on this picture is the atomic potential V of R plus the laser-atom interaction, which distorts the atomic potential. So one of the wall is going up while the other is going down. So suddenly we have a potential barrier here, and the electron in the ground state can tunnel through the potential barrier. We are in the realm of quantum mechanics here. When the electron is out, it is being driven by the laser field, and then laser field changes of sign, and the electron is being pushed back towards the atom and acquires kinetic energy. And when the energy meets the atom again, there is a possibility for the electron to recombine back to the ground state and at the same time to emit a short light pulse. This is a fully coherent process. You can think of a wave packet coming out, coming back, and recombine back to the ground state, interfering back to their ground state. how do we go from the emission of these attosecond pulses to high-order harmonics? This is what I am illustrating now. So I'm looking at these different electron trajectories coming back with slightly different energies, leading in the time domain to an attosecond light pulse. In the frequency domain, we have a broad spectrum. Why a broad spectrum? Because you have several electron trajectories where the electron is coming back with a different kinetic energy. And you can also think equivalently that the emission is happening during a very short time. So in the frequency domain, this is a broad spectrum. This process happens half a laser period later on the other side of the atom, as shown here, leading to another attosecond pulse with the assigned flip. So now what happens in the frequency domain? The spectrum is modulated at frequency 2 omega, where omega is the laser frequency. This process is repeated many times, leading to sharper harmonic peaks. So what you have here is it's actually very similar to diffraction via multiple slits in the spatial domain, leading to interference in the far field. Here we have a series of slits in the temporal domain, leading in the frequency domain to interferences. And these interferences are our odd order high harmonics. Let me say a few words about phase matching, about the macroscopic aspect of this phenomena. In order to have phase matching, what you want is that the phase velocity of the fundamental field propagating in the medium equal to the phase velocity of the harmonic fields. In other words, you want the refractive index at the fundamental frequency to be equal to the refractive index at the harmonic frequencies. So let's look at the variation of the refractive index over a broad range of frequencies. And you see that the refractive index in the region where we have our lasers is always larger than 1, while for the harmonic frequencies, we are in the ultraviolet, extreme ultraviolet, it's less than 1. So if you simply look at the effect of dispersion of the neutral medium, then phase matching is not achieved. Fortunately, there are a few electrons which are produced in this interaction, and these electrons add a negative term to the refractive index at frequency omega, which means that N0 here go down, and you see that then we can achieve phase matching. And this is happening for a degree of ionization, which is just a few %. If you have no ionization, phase matching is not achieved. If you have a lot of ionization, phase matching is not achieved. So this process happens over a small intensity window. The intensity needs to be high to produce high order harmonics, but not too high in order not to ruin phase matching. In 2001, there was really a breakthrough in our field of research with the pulse measurement and of attosecond pulses, and also the production of isolated attosecond pulses. And this was due to my two colleagues that shared the Nobel Prize with me, Pierre Agostini and Ferenc. Pierre Agostini could measure attosecond pulses in a train of pulse using an interferometric technique, which I'm going to describe in a moment, and Ferenc using a very short light pulse to begin with, could generate a single attosecond pulse and measure it, again by almost similar technique based on cross correlation and laser-assisted photoionization of a gas combined with photoelectron spectroscopy. So I'm not going to describe in details these two methods. This result was really important because it really showed that yes, it was possible to generate attosecond pulses through this interaction between a gas and a strong laser field, and through this process of high order harmonic generation, and really opens up the field of attosecond science. So I'm now coming to the last part of this talk, which is about study of electron dynamics. I'm going to show you two examples of measure that we can do thanks to our attosecond techniques. And I'm going to concentrate on the photoelectric effect, where atoms or material absorb light and electrons are being emitted. This effect was discovered by Hertz in 1887 and understood by Einstein in 1905. And this is actually why he got the Nobel Prize. So when Einstein explained the photoelectric effect, he was concentrating on using the quantum property of light and the concept of photon to explain the effect. We are going to focus on not on the light, but on the photoelectron. Maybe you think of this photoelectron as a particle going to a detector, click, and you can determine its energy, its momentum. But thanks to our attosecond technique, we can actually measure the wave properties of this photoelectron, its phase. You know that it's, of course, both a wave and a particle. And I'm going to discuss this electron really as a wave. How do we do this type of measurements? We use our train of attosecond pulse, our series of attosecond pulse in the frequency domain. This is the spectrum of high-order harmonics. And we ionized a gas and produce electrons. Well, if you only use this light, actually you don't get any temporal or phase information. You can only measure electrons at certain kinetic energies as shown on this slide. So our tool is not only these attosecond pulses, but also a probe field, which is a fraction of the field, the laser, which is used to generate the harmonics. In the time domain, it's an optical wave. And thanks to this additional field, we can have two photon ionization processes, creating sideband peaks. So here, for example, you have absorption of one harmonic plus a laser photon, and you obtain this sideband. This sideband can also be reached by absorbing the next harmonic and emitting, by stimulated emission, a laser photon. So you see that now we have two quantum paths going to the same final state. This is quantum mechanics. We add amplitudes of this quantum path, and the signal that we get is going to depend on the relative phase between the two amplitudes. And this allows us to get phase information. In order to see interferences, you would like to have something varying in this quantum interferometer. And what we vary is the delay between this optical wave and the train of attosecond pulse. The technique has been used by Agostini and co-workers and called RABBIT, which means reconstruction of attosecond beating by interference of two photon transition. How do we do that in practice? We need an optical interferometer, which can be a Mach-Zehnder type of interferometer, as you see here. So here the laser is split into two. In one arm, harmonics are generated in a gas cell, and then the fundamental field is removed by using a metallic filter. So you get a train of attosecond pulses. And then we have, in the other arm, we have a delay stage where we delay the the light here relative to the attosecond pulse train. So again, our tool is the train of attosecond pulses plus the optical wave with a variable delay. Then we focus this radiation using a mirror into a vacuum chamber where we put the gas that we want to study. And then we detect the electron using, for example, here, time of flight spectrometer. So we do electron spectroscopy. What do we see? This is a spectrum. It's called rabbit spectrum. So what you see is electron spectrum as a function, which are in color, as a function of delay. And you see several peaks corresponding to absorption of harmonics or absorption of or sideband generation. And the sidebands here are separated by twice the laser frequency, 3.1 eV in our case. And the information is actually contained in the oscillation of this sideband, as you see here. And the difference between two maxima here is, again, this half laser period, 1.3 femtosecond. So you see that our variation of delay is really in the attosecond time scale and needs to be extremely accurate. So here I kind of summarize the idea of our measurement. We produce an electron wave packet, a broadband electron spectrum, which is represented in blue here by absorption of train of attosecond pulse or these high order harmonics. And we probe this wave packet not only in intensity by measuring the amplitude of the different peaks, but also we measure its phase or the variation of the phase using this interferometric technique, using this addition of this probe field. So our signal is an interference signal that can be written as followed. And the interesting information is in the phase variation of these sidebands or the delay. This delay contains two terms, essentially. One, which is due to the excitation pulse, and this shows how the technique was used in the first place to measure attosecond pulses in a train. And then there is a group delay due to the ionization process. And this is the interesting term in this study. How can we measure it? Because we have two unknown quantities here. Well, we can compare two ionization processes in one gas that we want to study and in another gas where we know how to calculate this group delay, or we know that it's very close to zero. So this allows us to calibrate the influence of the excitation pulse. On this picture, I give you a little bit of physical interpretation of this group delay due to ionization. It's actually called the Wigner delay because it was introduced by Eugen Wigner already in 1955 as the derivative of the scattering phase. Here we're not talking about scattering, but photoionization, and this is half a scattering process. This is why you have a factor 1/2. Again, the physics is this delay is the delay for the electron to go out of the potential. And it's very sensitive to details of the atomic potential or molecular potential. Let me give you an example. We talk about xenon in the 4D shell, xenon photoionized in the 4D shell. Here I present very old measurement of the cross-section as a function of light frequency, light photon energy. And what you see is a broad resonance, which peaked around 100 eV, which was interpreted at the time in terms of a giant dipole resonance, a kind of collective effect of the 4D shell. But now we would like to look at dynamics of photoionization, look at ionization in the time domain. So how can we go from the time to the frequency domain? Mathematics, I would like to do a Fourier transform between frequency and time to look at the dynamics of this process. Well, what is missing using this result is the phase, or the derivative of the phase, which is the group delay. And this is what we can measure now thanks to our Attosecond techniques and thanks to the method I already described to you. Here is a result showing you this delay as a function of photon energy up to the peak of this giant dipole resonance. And this is for the 43½ electron. And we calibrated this result using measurements in neon. And what you see are positive time delays around the this giant dipole resonance phenomena, as well as a high delay at the threshold for 4D ionization, which we interpret as due to a spin flip due to the spin-orbit interaction, leading to a long delay. And we can relate this measurement to really the physics of the photoionization process. At threshold, the electron is really trapped in the potential. It takes a long time for the electron to go out, while in the region of the giant dipole resonance, there is an effect of trapping as well. The lifetime is non-zero, but it's reduced, and the dynamics is much faster. Let me give you a second example, which is resonant ionization of helium. So in this case, we create a narrower in frequency photoelectron wave packet by ionizing helium with just one harmonic. But we ionize close to a discrete state, here, doubly excited state. So here you have a beautiful and well-known example of a quantum interference process in atoms, and this problem was actually studied and solved theoretically by Ugo Fano in 1961 in a very well-known article. It's a beautiful example of quantum interference where the atom can be ionized directly to the continuum or can be photoexcited, and then you have auto-ionization leading to, again, an electron in the continuum. So you have two ways to reach the continuum, either directly or via the excited state. What we can do, thanks to our technique, is to look not only at the intensity of the photoelectron, but also at its phase, again using this interferometric technique, using another harmonic here and mixing with the laser field. And on the right, you see measurements showing the amplitude across the resonance with a beautiful interference pattern. And also, for the first time, we could measure the phase variation across the resonance with here a phase jump of pi. So when you have both phase and amplitude of this photoelectron wave packet, you can go now into the time domain and look at the dynamics. You can even do better, which is to use a time frequency representation of the photoionization process, which is shown here on the right. And here we use a Wigner distribution, which is defined here. And what you see on this plot, you see energy and time, and in color, you see the strengths of this distribution. What this shows is that at short times, you have this broad yellow feature, which is characteristic of the direct photoionization process. At a little bit longer time, you have a strong interference mechanism with yellow and blue blue is negative, so it's a strong interference. And this is when both paths are comparable in magnitude. And finally, at longer time, you have essentially ionization via the excited state. And this process is narrower in frequency and takes also can happen during a longer time, which is what you see here. So we can really follow in time the photoionization mechanism. So I'm now coming to the end of this talk. Let me say that Attosecond science is very, very broad. It's opening up towards many directions. I showed you some example in atomic spectroscopy, but there are also many ideas to use our technique in chemistry and in condensed matter physics. There are a few industrial applications, and there is also a very interesting interface towards quantum information. I have discussed attosecond sources by high-order harmonic generation in gases. We are in the extreme ultraviolet range, relatively low energy per pulse. We can work you can have your own laboratory in your university, but you can also use attosecond pulses by harmonic generation at different facilities. For example, the extreme light infrastructure facilities in Europe, which are completely open access for everyone. You have an idea, you just write an application and go there, and it costs nothing, of course, except the travel. So if you are interested by this physics and you don't have the infrastructure, I really recommend this possibility. And also, there are now attosecond light pulses produced by free electron lasers. These pulses are in the X-ray range, higher energy per pulse, and this is rather new. It has happened the last 2 years, and it's really moving very fast. And same idea, free electron laser are huge facilities. You can apply it for beam time with an idea, and you go and perform experiment at free electron laser. And with that, I would like to conclude this talk. Let me show you just for making you dream, maybe. This is a picture of the Nobel ceremony in Stockholm. And this is where I got the Nobel medal from His Majesty the King of Sweden. This is a picture of the Nobel banquet, which is just a few hours after the Nobel ceremony, and I had the chance to sit close to the King of Sweden. With that, I would like to thank you very much for your attention. I'm showing here a picture of the group in Lund with whom I am working, and this is a picture in front of the physics department where we do experiment. I'm happy to be part of a celebration of the International Year of Quantum Science of Technology, and as always, important to acknowledge organization financing this research. So thank you very much for your attention.
Thank you so much, dear Anne. It was, dear Dr. Anne, it was very enriching and beautiful, and with such uplifting images of you getting the Nobel Prize, which I'm sure will empower all our Gazan listeners, that the next will be you guys. I will now, thanks again, Dr. Anne. I will now pass the floor to Claire Roussy and Pierre Jamet, who will be your respondents and take questions from the audience. Thanks again. Pierre et Claire, c'est à vous.
Yes, thank you very much. Thank you for this talk too. It was quite interesting. There's a first question which has been asked couple times now regarding the applications to attosecond physics to quantum information, quantum computing. Do you have some more context and information about this?
Yes, it's not. We are far from helping for quantum computation. What we are learning to do is actually there are several actually many ideas. It's very open. The ideas coming from everywhere in this field. But what we're doing in Lund is to measure not only the amplitude and phase of the photoelectron, as I described, but the quantum state, the density matrix of the photoelectron. So it's really interesting to be able to do that. And in addition, we can in some case, we can see effect of entanglement of, for example, between ion and electron, and we have the possibility to follow this in the time domain. There are also ideas to produce harmonics which are non-classical field of light, so highly non-classical field of light. This is also an idea which is which is being discussed. So we are far from being, I would say, useful for quantum information, but it's very exciting field.
Okay, thank you. And continuing on the prospects, future prospects of this physics, do you think we will begin to probe shorter pulses than attosecond? What kind of physics could we probe with this?
Yes, first of all, I can say that the record these days is 19 attosecond. This is the shorter pulse that can be produced. What we can probe is electrons in inner shells. For the moment, it's electrons in the outer shells. So if we have a faster time scale, we can go into the inner shell. Possibly we can look at nuclei. This I don't know, but there is certainly a part of the community trying to get shorter and shorter pulses.
Is there a limit to the duration of the pulses?
There is, I don't think there is any fundamental limit yet. For example, we can produce harmonics which are really very broad plateau and corresponding to very short times. But the difficulty is to synchronize all these frequency components of this plateau. So this is more a technological problem rather than a fundamental limit.
Okay, thank you. Claire, do you have some questions?
Yes. So first, thank you for this very nice talk. There is a question about can this attosecond spectroscopy can it be applied to study correlated materials, for example?
Yes, absolutely. And it is already applied to study quantum materials or this physics is really starting, and there are two ways you can do that. One way is to not to generate in a gas, as I showed, but to generate in a thin film of this material, and to get information from the harmonic generation spectrum that you get.
Mm-hmm.
And the other possibility is a little bit like I showed. You send this harmonics or this attosecond pulse into a material, and you look at the emission or the absorption.
Okay.
And there is a lot of research in this area.
Okay, thank you. Another question is more about like this observation. Do they challenge like the classical description of electrons as a localized particle? Like, what is the role of the atomic structure in shaping the temporal identity of electrons during the ionization?
I would like to say that yes, it challenged this classical interpretation of the electron are as localized particle. We're dealing with electrons which are waves. So to me, electrons are like waves much more than. But of course, I mean, we are really in the middle of the particle wave duality, and it's very interesting.
Okay. And there is a question about can these attosecond pulses be used in the context of optomechanical system, for example, like to prepare a quantum state? Or no?
This is an interesting question, and
like can this be used with mechanical oscillators, like in optomechanics sometimes?
I don't know.
Okay.
It has not been done, at least.
Okay.
This I can say.
Okay.
Interesting idea.
Thanks. Pierre, do you want to follow up?
Yes, I can. So you mentioned briefly an analogy between the generation of higher harmonics and diffraction or interference patterns. Is there some implication about because it's interference in the time domain, if I understood correctly? How do you or is the analogy really there? And if so, do you use retrocausal waves or an interference between waves propagating in time in two directions in time to explain this?
I would say no, but I mean, it's more than an analogy. It's really what it is. It's an interference. And you can think of it as interference in time or interference in frequency. So, but no, as far as I understand, we don't need to go in the other direction in the time domain. No.
Let me see. So there were also questions about, if I can find it, about the way we visualize the dynamics of electrons and their movements inside the atom. Has this physics shed some light, new light into their motion, if we can talk about motion?
Yes, absolutely. This is a very good question. I have another example which I didn't show, but thanks to a measurements, we can really tell the theorist, but what we measure, your theory is not good enough for explaining our measurement, and for example, the example I'm thinking of is the description of minimum in the ionization of argon in the 3s shell. This was very well a success of the theory in the 70s with a theory called random phase approximation with exchange for the cross-section. So description of the cross-section in the 70s, theorists say, okay, now we understand it, we can describe it. This theory predicts now for the delay, which is what we measure, predicts a very long delay of like 300 attosecond. Takes a long time for the electron to be ionized. And our measurement show a minus 300 attosecond. So it's just the opposite, a push of the electron out of the potential. Thanks to that, we could tell the theorists, hey, there is something missing in the theory. And recently, a new theory came up with more correlation effects, and which could reproduce the experimental results. So certainly, we are asking questions to theorists. We are measuring something which was not known before. And what we are measuring is this phase of the photoelectron, not only the intensity.
Okay. Maybe one more question, which is a bit more general. What you showed involves many fields of physics. So you have optics, quantum mechanics, spectroscopy, and sometimes chemistry and so on. What kind of studies would you recommend to someone, to a young student, who would like to work in this field?
I would say it's very open. I think there is a lot to do in chemistry and condensed matter. I think if this physics is going to have an impact for the future, is really to look at processes in time induced by light interacting with materials. So this is going to be a big, I think, application. Then there is this interface with quantum information, which is also fascinating, but it's very difficult to predict where it's going at the moment, because it's very new and it's going into many directions. So what I want to say as well is that as I showed you a little bit, this field depends very much on laser technology, and lasers are progressing all the time. So this field evolves naturally because we have better and better laser to work with. And nowadays there is new lasers based on ytterbium technology, which are very much easier to use than the laser we have used in the past. So yes.
Okay. Claire, do you have some more questions?
Yes, there is some questions about how this high energy radiation can interact with electrons, but in biological cells. Like, can it be some application to improve radiotherapy or so? Others?
I am not sure, because we are not hard enough energy to be so our radiation is really absorbed by liquids.
Okay.
But so I'm more thinking in more looking at interaction in molecules, something like that, but not really in cells. At least this is what I can say for the time being.
Okay, so you mean you can only, for example, study a gas or?
Yes, or solid targets. So it could be molecules on the surface, for example.
Okay.
But not liquids.
Okay. And there is an interesting question about can you explain more about the spin flip that leads to a longer time delay before the resonance?
Yes, this is a very good question. I actually wish I knew the answer. So the only thing we can say that this is a region where we need to change from the LS coupling to the interaction coupling, and obviously I think we have some spin flips, but I'm not able to say much more than that, unfortunately. So be my guest and continue thinking about that.
Okay. I'm looking if there is other questions. Well, there is a question, what is the ingredient to get a Nobel Prize? But I guess no one knows.
Well, I can give you a try.
Okay.
You need to be a little lucky, as I was. And I think the second ingredient, you need to be very obstinate and really go for what you believe.
Okay. Thank you for this lesson.
Thank you very much, dear Claire and dear Pierre, for being respondents. And thank you all for your very valuable and insightful question. Above all, thank you, Dr. Anne, for your talk and for your insightful responses. And I think what you said, that in order to get the Nobel Prize, you need to be lucky, but resilient and obstinate. I think this is what Gazan universities, Gazan scholars, and Gazan students have shown. So as I said, we trust them to get the Nobel Prize next. I think we will stop here for now. Thanks again to all of you. As stated, the talk will be online on our dedicated YouTube channel. We can also deliver attendance certificates. Remember that science is universal, and universities everywhere in the world and in Gaza in particular should keep on working. So this is what we're here for. Dr. Anne, thank you so much. It was infinitely precious and so interesting. And thank you to all of you. Our next talk will be hopefully early December with Dr. Esther Duflo, who is also a Nobel Prize and also a woman. And she is a Nobel Prize in economics, but you will be kept updated. Thanks again, Dr. L'Huillier, and we will be in touch with all of you very soon.